Part 2 of Lesson 9. And the first thing we're going to talk about here is what a Coulomb is in terms of its magnitude or its quantity. And it says you might have noticed in the first example we did microcoulombs, right, which is mu c microcoulombs, and this is the kind of charges that we're talking about in everyday life right here. Only really special cases have charges of 1 or 2 coulombs, like a lightning bolt, right? So if somebody says to you, I'm going to punch you with 1 Newton of force or charge you with 1 coulomb of charge, go for the 1 Newton of force, because 1 coulomb is going to provide electrostatic force that is can be quite painful. Then there's this very important thing for Physics 30, which is the charges of subatomic particles of an individual. So an electron has a charge of negative 1.6 times 10 to the negative 19 coulombs, so extremely small, which makes you think, if that's the case, how many electrons would you get in a lightning bolt? And the answer is pretty crazy. So you can figure that out on your own. Maybe we'll do it later if we have an opportunity. How many electrons are in a bolt of lightning if it is 1 coulomb? A proton has the same charge, but it's opposite. And of course, a neutron has no charge. And in a later physics lesson, we're going to go over how these numbers were determined by Robert Millikan, and another outstanding physicist, and he devised a brilliant way of finding out what the charge on a single electron was. Here, well, okay, speaking of, maybe I should review the notes before I do the video. There it is. There's the answer. There's the answer to how many electrons would there be on a bolt of lightning or something that has a charge of negative 1 coulomb, and there's your answer right there. 6.25 times 10 to the 18 electrons. That is a lot of electrons. So again, if somebody says, I'm going to, for your birthday, give you 1 coulomb of charge, you politely decline. And don't ever talk to that person again. Keep in mind, okay. Then there's this little section on comparing electrostatic forces to gravitational forces, which we've kind of already done. So there's the formula. We're not going to go over this in great detail, but we will discuss this right here. Right, the gravitational constant is very small. Remember, this is the gravitational constant of the universe. This is the K value, or the electrostatic constant, and those numbers are wildly different. One is times 10 to the negative 11, and one is times 10 to the positive 9. So one is infinitely small, the other is essentially infinitely big, and therefore gravitational forces are very weak and electrostatic forces are very strong, which, if you remember the first video that I did, I was charging that pith ball, and then it was sticking to the glass rod, and that explains why that tiny little thing can defeat the entire gravitational field of this planet, because of that very concept. So electrostatic forces are very strong compared to gravitational forces, even though gravitational forces keep the entire universe intact. All right, now here we go. So here's more of a diploma type question, or a question you're going to get on the test, and that is to find the net force on a specific charge. And welcome back, vectors. This is a one-dimensional vector problem. I'm sure you remember in Physics 20, you always told, oh, vectors, they're going to come back. Yep, they're going to come back again and again and again and again. When you least expect them, a vector problem shows up. Here it is. So this is a one-dimensional vector problem. Determine the net force acting on the charge at the far right. So we are trying to determine the net force acting on this. And what we have to do here is we have to consider the forces individually. So what we're going to do is we're going to calculate how much the force between this particle and this particle is. Then we're going to calculate what's the force between this particle and this particle. should say this charge and this charge, and then we're going to add them vectorially. Right? So we essentially pretend that the other charge doesn't exist while we're calculating the charges between them. Right? So here's how I'm going to set it up. You can set it up any way you want, but I'm going to say the electrostatic force between Q3 and, we'll do this one first, in Q2 is going to be K times the charge of Q2, Q3, that'd be 3.5. And notice I am not putting in the negative, right? That you are going to confuse yourself if you start putting those negatives in. I'm going to divide that by the distance between them, which is 1.7 meters. And then I am going to determine that the answer between those two is 2.5 times 10 to the negative 1. Now, what direction is that? What direction is that? So what we do, we ask ourselves, we're talking about Q3. So this Q3 will get pushed which way by Q2? They're both negative, so it's going to get pushed this way. So I'm going to put to the right. Right? And that's how the negatives play their role. This one's negative, this one's negative. They're going to repel each other. And I ask myself, I'm talking about Q3. So I ask myself, which way will Q3 be pushed? It will be pushed to the right. Then I'm just going to repeat the process for Q1. So FE, Q3, and Q1. Right, so we're going to get, again, we're going to get the K value, and we're going to just plug in the different numbers. That's 3.5 times 10 to the negative 4. This time we got 1.5 times 10 to the negative 7 divided by, be careful here, because the distance between them is not 1.4. It is this whole blue line here, which is, what's that, 3.1 squared. Okay, so be careful that you get the distance. Remember, we're totally ignoring Q2 at this point. We've already done Q2. We're going to calculate that to be 4.9 times 10 to the negative 2. Now, which direction is this one? And again, we're talking about Q3. This time, this is positive. This is negative. They're going to be attracted to one another. So in other words, Q3 will move to the left. So I put left. One to the right, one to the left. Q3 gets repelled by Q2 because they're both negative, but it's attracted to Q1 because they're opposites. And now I just add these two vectorially. So I'm going to say that the net force, the electrostatic net force, equals 2.5 times 10 to the negative 1 plus negative, and you, of course you're saying, well, not of course, you're probably not, but you may be saying, well, why'd you put the negative in there all of a sudden? You keep telling us don't put negatives in, but now we're dealing with the net force, and now we must indicate that they have they have different directions. So one must be positive, one must be negative, because one is to the right and one is to the left. So that's where the negatives actually are very important. And if you add those two together, you will end up with 2.0 times 10 to the exponent negative 1 newtons. And since it's positive, and we designated right as being positive, then it is to the right. Okay, so the electrostatic force is kind of Q2 wins out here. It's much closer, so its electrostatic repulsion is greater than Q1's electrostatic attraction, and therefore Q3 is going to end up going to the right. That is a one-dimensional problem. Now we go over to two-dimensional problems. Wow, just like all the vectors we did, and just like momentum. This looks similar to momentum. two-dimensional vector problem, but this time with electrostatic forces. We're going to do it the way we've done all others. In this question, we're asking for determine the force on Q2. No, always kind of circle that, Q2. And they've been very merciful to us in this problem and given us some nice, easier numbers to work with. Although again, we're talking about lightning bolts here. This one is specifically, especially aggressive. And 4 coulombs of charge is a lot of charge. That's a lot of electrons. And before we do this, let's just rationalize or hypothesize which way do you think it's going to go. First of all, they're all positive. They're all positive. So in other words, these charges are going to repel one another in a big way, especially since they are all have such a high value of such a big quantity of charge. So Q2 is going to get pushed which way by Q1? Well, they're repelled, so it's going to get pushed down. Q2 is going to get pushed which way by Q3? Well, again, they're repelled, so it's going to get pushed that way. If we add those two vectors vectorially, the vector sum of those is going to be approximately, right, tip to tail, 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 tip, tip. It's going to be approximately in that general direction. Now, it's a very general answer because this one here is closer. It's closer, but it has less charge. This is further away, but it has more charge. So we don't know if it's going to be like 45 degrees or what angle it's going to be, but we know it's going to go in that general direction. And now we can do the problem, and we do it similar to the way we did the first one. We can say that the electrostatic force between, we're dealing with Q2, so I always put Q2 first. Q2 and Q1 is going to be K. I'm just going to abbreviate here a little. K1, oh, this is nice, 2 divided by 3 squared. And we're going to get that electrostatic force, and it turns out to be 2 times 10 to the 9 newtons. So that's a lot of force. A lot more than the 1 Newton force of punching you in the face. I should not use these examples. We've done that. So that, I want to say, which direction is that? Which direction is that? And that is they're repelling because of the same charge. So that is going to be down. Or you can just do it that way if you want. Now we're going to do the same thing with Q2 and Q3. Okay. This one's 4. Sorry, I did that wrong. I should have done the 1 first, just to be, doesn't make a difference, of course, mathematically, but just to be consistent. Q2 is 1. Q3 is 4 divided by, oops, ran out of room here, divided by 4 squared. And that is going to give you 2.2 times 10 to the 9. 2.2 times 10 to the 9. And again, they're repelling, so it's going to be to the left, down and to the left. And now we can add those two vectors, just like we did over here. Just like the vector sum, it's getting pushed this way and it's getting pushed this way. We put them tip to tail, resultant vector, find the angle, find the hypotenuse, and get your answer. Let's just do that separately though. So now we have one vector going this way, the one to the right, to the left, because I always do my horizontal vectors first, is 2.2 times 10 to the 9. The one going down was 2 times 10 to the 9. And find the resultant vector, the resultant angle always between the two tails. Resultant angle always between the two tails. Use Pythagorean theorem. Right, so it's going to be called the square root of 2e9 squared plus 2.2e9 squared, and that gives you 3 times 10 to the 9 newtons. That's a nice number. 3 times 10 to the 9 newtons. And the angle, inverse tangent of 2e9 divided by 2.2, opposite divided by adjacent, e9 gives you an angle of 42 degrees. 42 degrees. Now, in the question, they don't give you any kind of direction, so you'd be free to put your direction in a multiple ways. I would probably say 42 degrees below the horizontal. No, I wouldn't say that, because then that doesn't indicate if it's left or right. I think you would have to actually go 42 degrees south of west. So the final answer to the question, 3 times 10 to the 9 newtons, 42 degrees south of west. That will be sufficient. So there we go, two-dimensional, one-dimensional and two-dimensional vector problems involving electrostatic forces. And we'll see you for lesson 10.